Hi, guys. So yesterday in the middle of the night, I posted some data from the Cavendish experiment. I'd come in and gotten the laser up and going and let it sit equilibrating. So this laser, like all Heaney lasers, like all gas lasers, is going to be prone to some thermal issues. And we can actually study that pretty closely using a Fabry-Perot cavity, which would allow us to study the frequencies, the emission lines of the laser, and we would see them move around as a function of the change in temperature inside that laser cavity. So one of the consequences of that, putting aside the laser's operation in a more fundamental sense, is that you get beam steering issues. So as the laser heats up and cools down, it'll tend to fluctuate its cavity length and also the exact angles that those mirrors are at, and that will change the steering of the beam as it comes out of the laser. So that's one possible source of drift in this experiment, right? The actual pointing of the beam could be fluctuating. It's probably a small amount, milliradians, I would start as my guess, but it can add up when you have a beam path that's many meters long. On top of that, we talked about some other possibilities for sources of instability in the system, the kind of janky way we had the laser mounted, and then the Cavendish experiment itself. There we go. Right there. So that guy is also kind of mounted a little bit janky right now. And as a consequence of all these factors, I observed that the beam wandered around pretty substantially, right? So yesterday, over, 5 or 6 hours, the beam had wandered around through those different spots. That's a lot of excursion. I mean, that's 6 inches of width. And it could be the case that the beam actually wandered off further than that, and I just didn't see it. I was doing some other work, so I was hopping back and forth between the laser lab and my office, and maybe the beam wandered another inch off to the left, and I just didn't catch it. Okay, so we know that there's real drift in this experiment, and the data I posted shows that. You can see a very clear oscillation. It's a damped harmonic oscillator, but there also seems to be some curvature to it. And it could be that we can cope with that by just adding in a drift, a linear term, just some function like that, or maybe even a quadratic or something to account for that drift over the course of the experiment, and just let the fit beat it out. That would be a fine way to approach it for a first analysis. We could also take the time domain data, Fourier transform it over into the frequency domain, and try to filter out any components that don't occur at that expected oscillation frequency. And we know what that is, right? It's going to be the square root of k over I, where I is the moment of inertia and k is this torsion pendulum spring constant. It's not newtons per meter. It's Newton meters per radian now. Okay, so we can figure out what the frequency of oscillation should be, and then filter out any Fourier components that occur at different frequencies, transform back to the time domain, and then when we do that, we should have a signal that's just well-behaved oscillation, right? That's a lot of processing to be presumptively doing, but it'll work. It's actually not even that much, really. I mean, you can make a pretty good argument for doing so. Anyway, so we can totally work with that data. I showed it to Dr. Choka, and he was chuffed by it. He was really well pleased to see that kind of result, because they'd struggled to get this experiment to do much previously. I also mentioned that the result was promising to Dr. Yoder, and he told me that when he was maybe a grad student, maybe an undergrad, one of the institutions he was associated with, they'd had to work out what the schedule was for the freight trains on the nearby railroad lines, because it was perturbing their Cavendish experiment. So I think you can glean from that we're getting pretty good results here. I'm going to run another trial now, right? So we'll create another set of data. I had yesterday figured a good way to do this was just to tape that 72-inch yardstick to the wall, as opposed to trying to draw circles and keeping up with that and trying to write down the time as it happened. It was way more effective just to watch the spot, pass through the 32nd inch or whatever and then write down the time that it did so. So that worked great last night, and I'm going to do the same thing again. The numbers will not be directly comparable because in the middle of the night, the ruler fell off the wall. It was just taped up there, which would have been terrifying for anyone in here. But fortunately, I had gone home. All right, so we're going to run another experiment, and I'll upload that data, and we'll see, again, what does the drift look like? It'll be an interesting result. All right, so hang on. Okay, so sorry about that. I just noted the equilibrium position of the spot on the wall. It's over there. Then I moved the forcing masses to the opposite side of the Cavendish pendulum. And now the spot is bopping along. So you can see there's some vibration to it, but it's also moving. So we're going to track that motion, and we'll record some data. Okay, guys, it seems to me that the drift in the spot is now comparable or larger to the clear oscillatory motion. So I'm going to wrap up this measurement, and then I'm going to upload these data to the Blackboard site. I would say that the error in assigning times to those positions is probably about plus or minus 1.5 to 2 seconds. And that's based on two effects. In the beginning, there's this epicycle motion to the spot. And that's because it has a wiggle from the bump of moving stuff around on the table when I rotated the masses. At the end, it's just that it's creeping so slowly. So as the spot, which is yay big, aligns with the hatch mark about that big. Is it there yet? Is it there yet? Is it there yet? If it sits there for a second, by eye at least, when do I mark that time? So I'd say it's probably plus or minus 2 seconds of accuracy by the end of this run. So I think that's a good estimate for our error in our timing, from which you can work backwards to get an error in position if you want to use that as your variable instead. I'm not really being clear because I haven't really talked to you about the specifics about how you're going to calculate this stuff. But that is probably our key uncertainty. The other ones are going to be errors in the positioning of the forcing masses. So we can get the details of the geometry of this thing from that Pasco document, that PDF. But my problem is looking at that Cavendish pendulum, as I move the forcing masses, I try not to actually smack them into the glass because I think that's just going to cause a really huge wobble in my pendulum. So I think the issue is I try to get it just basically to within a hair's breadth of touching it. And I don't know how well I did that. So there could be an error of perhaps 0.5 millimeter to 1 millimeter in the distance between the masses on the pendulum and the forcing masses. So keep that in mind too. Okay, I'm going to go turn this into an Excel file. Okay, hi guys. I ran through the data and plugged it into a spreadsheet to get a preliminary graph. We'll need to analyze this in something more substantial, I think, just because it's a more complicated function than you'd want to mess with in a spreadsheet. We should be doing stuff like this in Python or some other numerical tool. But regardless, take a look at it. I think this result came out really well. There's less apparent drift in this run. One thing I should do is take a look at the temperature loggers for the optics lab to see if the temperature was fluctuating more substantially last night, because that would explain in part the greater drift we saw if there was more mechanical instability due to just thermal perturbation, right? Differential expansion of materials. All right, so I uploaded the data to the Blackboard site. I will upload this video momentarily. And a tiny little clip that I filmed showing the wobble in the spot as it moved back and forth. That was how I was figuring out what I thought a good estimate of the error would be in timing the spot moving across those hatch marks. All right, let's take a look at that.